Hello, this is Paul from Foresight Tech. In this video, we are going to deal with the chain rule, and which is probably the most important topic is in Calc 1. And let's going to see the material. Okay. And so first, I will going to introduce what's chain rule, and I will give you a proof as well. And then we have 3 problems, 3 questions to practice together. So first, what's the chain rule? Okay, why chain rule we call the most important topic is in Calc 1. So you will understand later. So first, what's chain rule? Chain rule is to find the derivative of a composite function. Okay, which means a tool to find the derivative of a composite function. Why this is so important? Because most of the function we deal with a composite function. Okay, so make sure this. So this is the most important. First, let's look at a notation. So the first notation we call the Leibniz notation. The later we have prime notation. You see, right? And the Leibniz notation. Excuse me. So you know who is Leibniz, right? Yes, it's one of the founder of calculus. Of course, you know. And the notation is like this. So first, we going to decompose the composite function into this way. What does this mean? And the y equals f at u equals gx. So if we plug u inside this, plug gx into u, so we have y equals f at gx, right? This we call the composition. The composite function f composed g. So f we call the outer function. Right, we learned from pre-calculus. So the inner function is u, or we call the gx. Can you see? F is outer, g is inner. Okay, if we already decompose, now Leibniz notation give us the formula is this way. What is the derivative of the composite, which is y? dy dx, right? dy dx, which means y take a derivative, or this composite function take a derivative. And of course, this is a Leibniz notation. How to equals, can you see? This is a derivative, okay, dy du, and this is another derivative, dy dx. So which means and the derivative of composite function is the product of 2 derivatives. Let's going to see what the detail. Dy du is this, dy du, which means what? Is the derivative of f, right? The derivative of f, which means the derivative of the outer function. How about the second derivative, du dx? Can you see ux here? So du dx is g take a derivative, which means that the inner function take a derivative. So here the second part is the derivative of the inner. The first part is the derivative of the outer. Okay, I already put the words. This is the most important part, and the pattern is easy. And the derivative of can you see the bottom? Derivative of a composite function, right, the left side, is the derivative of the outer function, dy du, times the derivative of the inner function, du dx. Can you see? Of course, the first is evaluated at the inner, because u is gx, evaluated u equals gx. Whatever, we can see this. This is the pattern. If I write it here, so the derivative of the outer, right, times the derivative of the inner, the product of 2 derivatives, which is the chain rule. Okay, that's what we call the Leibniz notation. Later we're going to prove this. First, so if we look at the Leibniz notation, someone know. Okay, Leibniz proposed the method, right? Okay, now in the history, we also have another version. Someone said another mathematician, Scottish mathematician, proposed the chain rule at the first time, who is called James Gregory, and is also a very famous guy. Let me write the name for you. If someone you like, you can go to Google. Okay, is James Gregory. Okay, and I think it's Gregory. Okay, you can Google James Gregory is also a very famous mathematician in the history. And at least James Gregory proposed the first time for the fundamental theory of calculus. In the future, we were going to learn this fundamental theory of calculus. Okay, so no matter Leibniz or James Gregory proposed the chain rule, at least we know Leibniz popularized this method, at least, right? And so far you see. And this notation was made by Leibniz. Okay, so this is the first. We're going to prove, of course. Let me see the pattern a little bit. If you look at dy du and du dx, if this is a fraction, of course, so far this is a derivative, not called a fraction, right? But however, in the future, we were going to define dy or du. This we call the differential. Is just a quantity, which means this we can see this derivative as a fraction. Okay, if this is a fraction, we can cancel the common factor du. If we cancel du, can you see this? Okay, if we cancel du, this is du. No. If this du and this du, if we simple cancel, what do we get? The left exactly got the right, right? Okay, so of course, so far we cannot see that, but when I give you a proof, so you see this is true. And we have the second notation we call the prime notation. Okay, can you see prime notation was proposed by Lagrange? I will going to show the Lagrange. So it's a Lagrange. Okay. And Lagrange was an Italian mathematician, also famous, and who proposed the prime notation. See, the prime was proposed by Lagrange. So the prime notation, sometimes we call the Lagrange's notation, or prime notation of Lagrange. And what is the notation? Is this? Can you see? And the left is exactly the left of dy dx. Y is y take a derivative, right? Which means find the derivative of composite function. Can you see the right is there are two derivative terms together. The first derivative is the order, right? F take a derivative. Of course, u is gx, so we plug gx here, which means the derivative of the outer, and the gx is the derivative of the inner. Can you see? And the prime notation is exactly the same material, right? The same content as the Leibniz notation. All the difference you see is the notation. And the prime notation is the most popular one so far we use. Okay, the Leibniz notation is the very original one. Okay, in the future we will gradually going to the prime notation. Okay, so in this video we were going to compare, okay, Leibniz notation and the prime notation, and later you will see both get the same results. Here is the basic knowledge. So now let's go to prove how to prove Leibniz notation. Can you see? And all we need first is we decompose. This is the most important step. Okay, the first decompose a composite function. So f is inner, and u or g is the f is outer function. So u or gx is the inner function. And all we need is dy dx. Use the definition. Can you see? This is the definition, right? The limit of the average rate of change is the instant rate of change, and the dx is the increment. What is dy? Can you see here? We define dy is the rise of f, right? So f at u plus delta u minus f at u. That's dy. So what is delta u? So delta u is the increment of the inner function. Okay, of course, which is g at x plus delta x. Delta x is the increment at the very beginning, minus gx. Can you see? Delta u is the increment of inner. Delta y is the increment of outer function. And we need this notation. So now we move to here. Can you see? We're going to step by step. So the first step is definition. The second step, we're going to do what? We put the delta u is a manipulation, right? So all we simply say is a manipulator. We're going to, this step is a manipulate Okay, so how to manipulate it? We times delta u to the top times delta u to the bottom, right? If you cancel delta u, definitely you get the original. And now is what we get. We get the limit of product. Limit of product, we can change it to the product of two limits, right? Okay, that's what we call the product rule. Or we simply say is the limit law. Okay, let me write it here. Now we can use limit law, product law. We can break it down into two limits. Okay, and the second limit you already have. Okay, so what are we going to do? Is going to deal with the first limit. Okay, you know what we are going to do. See, here is delta u. So the limit below the limit is delta x. Of course, we need to merge them together. So can we read this red one? So I will change delta x pos 0 to delta u pos 0. That's the only change we did. So why we can do this? Because of this. Can you see? Because. And the u, I guess the relationship is here. U is gx. Can you imagine if delta u is here, the increment of u? If delta x pos 0, okay, of course delta u pos 0. Because what? Because g is continuous. Why g is continuous? Because g is differentiable. Differentiable, therefore, is continuous. Let me write here. What do we need is this. Because delta u pos 0 as delta x pos 0, right? Why we have this? Because of g is continuous. I say is since g is continuous. You know why g is continuous? Because g is the inner function, so we need to take a derivative. Therefore, g should be differentiable. Differentiable, then continuous, right? If g continuous when delta x pos 0, of course, and this is delta u should be going to 0. Therefore, what we can do, we can change delta x pos 0 to delta u pos 0 because delta u pos 0, right? Okay, good. Now, what do we have? We have two limits, and each limit is derivative. What is the first limit? Delta y, delta u as delta u pos 0. What does this mean? This is the average rate of change, which is the limit, which is the dy du, right? Derivative of y to u. How about the second? Du dx, delta u delta x, which is du dx. Du dx is just the derivative of u, which is the derivative of inner. Can you see here is already the answer? Derivative of the outer times derivative of the inner. That does make sense? Therefore, that's the proof for the theorem. Okay. And now what do we left? Okay, is going to practice 3 questions together. I'm going to see the first question. Okay, is this one. We have 2 parts for these questions. We have the function here. The first question asks us to decompose. And you know this function is a composite function. Of course, we need to decompose, right? So it says the order is, we have to do this. We have to follow, decompose. The order is F. This is order. Okay, the inner, okay, so I can see the inner is G. Okay, we have to use this notation. First step, decompose. The second step asks us to find the derivative using Leibniz notation. Of course, the chain rule of Leibniz notation. After we use Leibniz notation, please look at the second. We're going to find the derivative using prime notation, which means the same functions. We have to use Leibniz notation to find the derivative, and also use prime notation to find the derivative. What are we going to do? Of course, we're going to compare, see if both methods get the same answer, or we're going to practice how to organize our work. Okay, so let me go to see. So the first step, decompose, and then Leibniz notation, and then prime notation. Okay, we follow this. Keep in mind that F is inner. No, F is outer, and G is inner. So the function is here. Let me work on Leibniz notation first. I need to copy the function. Okay, so I put the function to here. Let me see, y equals, and the cube root, right, of 1 plus 4x. Good. And then we move to this page. We can work together. The first step, remember, so find the Leibniz notation. We need to decompose. And from pre-calculus or at the first chapter, we already discussed this topic, how to decompose. And this is the very important step. And the decompose, all we need to do is find the inner, right, and then find the outer. Here is easy. See, if we set up this is the inner function is u, right? If we set up u is 1 plus 4x. Okay, plug u here, and then we get a cube root of u, which is the outer. That doesn't make sense. Very easy to decompose. Let me write. So this we call the decompose. Let me see. The first step, of course, is decompose. I wrote here. Decompose. And then we already wrote that the outer function is y equals cube root of u, right? Okay, I wrote here. So y equals cube root of u, right? And then u is the inner function is 1 plus 4x. That's good. This is the decomposition. Of course, somewhere like I will write a little bit. And the cube root I wrote into power. Okay, so you know it's the same. Is u raised to how many is power? 1/3. The power is 1/3. So that's the same. And you know this is the out. Why we wrote it into power? Because later to take a derivative it's easier. Okay, so this we call the outer function. So this is a outer function, right? And where is the inner function? Of course, this is the inner function. And both we need to use because now we're going to Leibniz notation. Remember, is the derivative of the outer times the derivative of the inner, right? That's all. So now I'm going to the chain rule to find the what? To find the dy. Okay, dx. Do you remember chain rule? See, we already finished the first step. So now we're going to the second step. And the second step is going to use chain rule. Let me write here. Right here is we're going to use chain rule. Okay, so the chain rule you remember is dy du times, right, du dx. If we cancel du, so we get the dy dx. So the pattern is super easy. And also we know the first dy du is the derivative of the outer. The second du dx is the derivative of the inner, right? Okay, good. Now all we need to do is plug what is the derivative of the outer, what is the derivative of the inner, right? Derivative of the outer is here. What is the outer function? U raised to the 1/3 power function. Easy, the easiest one. So I'm going to write what we have is this. Okay, we're going to write. Should it be here? Is how to take a derivative of the power? Take the power down, right? The power 1/3, so we wrote here. And then the old power minus 1, we get the new power. 1/3 is the old power. Minus 1, we get a negative 2/3, which is the new power. Negative 2/3, right? Parentheses. Can you see here is the first, the derivative of the outer. Our counter times the derivative of the inner. What is the inner function? Here is the inner function. Du dx is what? Du dx equals u take a derivative to x. You know what that does mean. 1 take a derivative is 0. 4x take a derivative is 4, right? So what do we get? We get a 4. Okay, so easy to get. See, almost. And then we put the 4 and the 3 together. What do we get? Let me see. Simplify a little is 4/3, right? Times u negative 2/3. And can we stop it here? No. Why? Because here is u. At the very beginning, the function is x. So we definitely need to go back to x. What the relation? The relation u equals 1 plus 4x. So we have to back substitute. Okay, so here is the last step is back substitute. So we say is back substitute. Okay, so what is back substitute? U is 1 plus 4x. So we plug u as 1 plus 4x in, right? So what do we get? And this is the answer. We get 4 over 3, right? Parenthesis 1 plus 4x. You know this, right? And then raised to the power of negative 2/3. So here is the answer for this question. You can go over. All we needed, the first step is decompose. The second step use the chain rule. The last step, don't forget to back substitute. And then whatever the answer we get is here. Now let me look at what is the prime notation. And after we get the answer, we're going to compare to these results. Okay, was prime notation. So remember the function. So I have to copy the function first. You see how we can organize this. All we need to do is this. Y prime, right? This is what we call the prime notation. And equals what is y. Remember, if someone remember, if you forget it, we're going to here. This is y. I copy all these functions, go down here because we need to use that. Okay, so now is here is q below, right? Is q below 1 plus 4x. This is the y, and put the parentheses, take a divider. Okay, so we don't like this way. We change it to the power. Okay, the same as we did before. Okay, I change it a little bit. I have to use this. Okay, this should be 1 plus 4x is the base. The power is 1/3, right? This is the basic definition of q below. Then take a divider. Okay, now all we need to do is this. And let me put, this is a composite function. Take a divider. Do we remember what is the notation? The notation is this. Divider of the outer times divider of the inner, right? Okay, so let me write here. So this is what? Divider of the outer times. And this is the divider of the inner. Okay, let me write a little bit longer. So what is here? We said this should be the derivative and of the outer, right? The outer function. I will write a little bit more words. And so here is what? Here should be the derivative of the inner function, right? Inner function. Okay, so now what do we do? It's just figure out what is the derivative of the outer and the derivative of the inner. You know what is inner, outer, we have to decompose. Of course, you know how to decompose. So here is a u, right? Let me write it here. If you work on the question, you don't need to exactly write all this stuff, okay? And for me, I just wrote this so you can understand. See, this is the inner, and after this, we plug u to here. What is the outer? The outer, of course, is u raised to the 1/3. See, this is the outer, and the first here, the box we need to put the derivative of the outer, right? So what is the derivative? Derivative of the outer is a power function. So we take down the power, and then the older power minus 1, which is a negative 2/3. Of course, we know u, right? So we plug u in is 1/3. U is what? Is 1 plus 4x raised to the power of negative 2/3. Can you see? This is the derivative of the outer, which means we have to put it here. Can you see? Okay, so now good. We put here is what? Is 1 third, right? Times 1 plus 4x raised to the negative 2 third power. So good that this is what we found, the derivative of the out. Okay, so don't put the u here, because what? If we erase all this stuff, we don't have u, right? You can imagine in your mind what is u. U is just 1 plus 4x. Now, what is the second box, which is the derivative of the inner? Now it's easy. The inner is just here, or u here. You can directly put the 4, but my suggestion is put one more step. Can you see? 1 plus 4x did the inner. Put the parentheses, take a prime. Why we do this one more step? You can imagine. In the future, if the composition is too complicated, we definitely cannot directly write down the answer. Therefore, we have to write this prime. Okay, so put here just, and then we do one more step to get the answer. What is the last one more step? Okay, so one more step should be the second derivative, which is 4. And the 4 times 1/3 is 4/3, right? So I put the answer is this 4/3, and then is 1 plus 4x and raised to the power negative 2/3. And this is the answer, whatever we get so far. But probably you will see, okay, so this is too complicated, right? Okay, so exactly when you work on this, how do you think? You do not need to exactly put the u here, derivative here, right? You can just ignore. And the same, you also can ignore these words. Okay, if you ignore everything these are wrote in the red, that should be, and what you need to organize your work should be easy. All you need to just imagine in your mind what is u. U is 1 plus 4. See this as a group, as u. So the outer function is u raised to the third power. Power take a derivative is power. The second is u take a derivative. Okay, so this is the prime notation. And let me show a little to you. And if we go into this, if I erase, okay, if I erase this, because this is what I wrote for you, and exactly when we work on questions, we do not exactly need to write that, okay? Write all this, you will see is how simple it is. And if I write, clear this, can you see? And this is all you need to do. Use the prime notation in the future. We will gradually go to this step, okay? But now, let me go back. I put everything I did here. And the last step, we're going to compare the two answers, see if they are the same. Okay, so can you see? What we get from Leibniz notation is 4/3, 1 plus 4x. Read this. Keep in mind that this is the answer from the first notation. Here is the answer from the second prime notation. Of course, they are the same, right? And probably you will say, look, both of the methods look almost the same, right? And I can pick any one. However, prime notation is much more convenient for a complicated composition, which means what? That's why the reason why prime notation is the most popular notation so far. Okay, so keep in mind we are going to use the prime notation for most of the questions in the future. We have another 2 questions to practice. Okay. And we almost, I hope you through this example you get something. Here I still going to write the Leibniz notation and the prime notation, okay? But I will take a little bit easy way, okay? So I will directly going to look at the composition, and this question is the same as question 1. So what do we need to do? They will ask us to decomposition, and then to find the derivative using Leibniz notation, find the derivative using the prime notation, and then we compare the 2 answers are the same or not. Okay, so let's move on. I think you already get the steps. All I was going to do is do this. So the first is decompose, right? Let me write here the same. what we're going to do is going to decompose. How to decompose? Of course, this is easy. We set up a u, right, is pi times x. This is the inner, therefore the outer is tangent to u. Okay, so I wrote at here. So our decomposition is y equals tangent at u. This is the outer function. The inner function u equals pi x. Okay, easy. And now I use the Leibniz notation, going to find the derivative. d what? dy dx, right, equals. Okay, we still need to write the chain rule. Let me write here. We're going to use the chain rule. We're going to use the chain rule. So what the first is dy du, and the second is du dx. If you already wrote this, you cancel du, definitely the same. I hope you already get this. Memorize this formula. It's super easy, right? Now all we left is what? Plug what is the derivative of y, what is the derivative of u, what is the derivative of outer, what derivative of inner. Okay, just like that. Let me put it here. And dy du, which means the derivative of tangent u. And I hope you remember the formula we used before, which is the secant square, right? Okay, so let me write, which is secant square at u, and the times what is du dx, and see the inner is here, is pi x, take a derivative. Everyone knows should be pi, right? Let me put here should be pi. This is a little bit confused. Probably you can use this. You can use the parentheses. Well, look, this is much better. And can we stop at here? No. What do we need to do? U is not what we need. We need the x. Back substitute, right? So all we need is back substitute. And here is a back substitute. Okay. After back substitute, see what I get. Easy. Okay, what I get it is pi, and this constant number I put at the beginning, times secant square at u. What is u? Pi times x. Okay, pi times x. Of course, we need to put a parenthesis. Can you see here is already the answer for the first part. We get the answer by using Leibniz notation. Okay, now I will going to use prime notation, see if we can get the same. You know, we should get the same, right? We should get the same. But how to organize this? Prime notation is use prime, so Lagrange, right? So all we need is y prime. So y prime was y. Let me copy. Y is tangent at pi x. See, this is y. Okay, I'll put this bracket. Going to take a derivative. Now all we need is write this. And this is a composite function, take a derivative. Do you remember the prime notation? Which is what? I have to write this. This is the outer, the derivative of the outer. Remember that? And then we times, of course I wrote a little bit longer. And then we times the derivative of the inner function. Okay, that's all. Okay, so what is the outer, what the inner? I think you can find this pi x, right? So let me write a little bit. So u is the inner. So what is the outer? Plug u here, tangent u is the outer function. So we have tangent at u is the outer function. So all we need to put at the first is the outer function, take a derivative. And you know the formula, which is secant square at u. What is u? Of course, we plug u is pi x, right? Okay, so here is a square. Okay, can you see this is the derivative of the outer? All we need is plug these results. Okay, so we're going to here as the first time we did. So I will put is secant square, right? So all we get is secant square at pi x. See, we already find the first part. So what is the second part? So we still follow the rule. I wrote one more step, which is here. The inner function is pi x u, right? Put the parentheses, take a derivative. Okay, can you see this is what we need to do? Okay, wrote one more step to get the answer. Pi x take a derivative is pi, so we put the pi at the beginning and then times secant square at pi x. Okay, so this is all. Can we compare now the answer? Of course, they are the same. Can you see? Use the prime notation, we get this. Use Leibniz notation, we get the same. Definitely they are the same. This is the second questions. I hope you know how to organize it now. Okay, so let me practice the last questions together. Here is almost the same step. If you get the chain rule, so it's very easy to do. Okay, the same. So we deal with this function. Of course, this is a composite function. Okay, and the first step we're going to decompose and then use the Leibniz notation, find the notation. The last is use prime notation to find the notation. Okay, the same. And excuse me. And all we need to do is decompose, right? Let me see the first. I was going to decompose. How? Okay, of course it's easy. Can you see? Here, if I set up that's u equals square root of x, and then we have the e raised to the u, which is the outer function. Outer function eu, which is the natural exponential function, and the inner function is the square root function. Okay, so easy to decompose. Now, what do we do? I wrote the decomposition, which is y equals u, right? This is the outer. The inner is u equals what? Square root of x. See, very easy to do. Now I can use what? I can use the chain rule. So let me write the chain rule. Dy dx equals. All we need is write the chain rule. Okay, let me write the words here. So now we need to use the chain rule. The chain rule is this: is dy du times du dx. If we cancel u, we get the dy dx. That's definitely. Okay, so after wrote the formula, now what we need to do is evaluate the derivative. Okay, the two derivatives. What is the first derivative, which is dy du? Dy du is the derivative of the outer here, right? Derivative of natural function is itself easy. The easiest derivative. So what we get is e raised to the u's power. If you like it, you can put the parentheses, and then we time what the second. The second is square root. Okay, this is a very popular functions, and the previous video I asked you to memorize. And this is a power function. The power is 1/3 and 1/2. Of course, you can use the power function and go through a few steps. You will find here is the derivative. Okay, is 1/2 times square root of x. Okay, so I want you to memorize these results before, right? Try to memorize this. Now, what is the last step? Okay, the last step, of course, don't leave here u. We don't need, we need x. So back substitute. So the last is this. We have to back substitute. Okay, see what is. Now we're going to put. So the denominator is 2 times square root. I just wrote this fraction. The denominator is 2 times square root of x. The numerator, of course, is e raised to the e's power. E raised to the e raised to the u is a square root of x. Can you see? Here is the answer, whatever we get so far. And then later we use the prime, we're going to compare. Okay. So, sorry. Okay, so now we're going to the second. So how to use the prime notation? You remember that I use prime, right? So I use a prime. Okay, so all we need is a y prime, and then now we plug y. Y is this e raised to the square root of x. This is y. Parentheses, take a prime. And then what to do now is easy. all we need to do is do this. And put the formula. Let me put the formula here. And this is the outer function. No, not the outer function. The derivative of the outer. Okay, and then times the second. And here is the derivative of the inner function. Okay, so we need to decompose. Of course, easy. And the power, right? That's u. Let me write here. So we can easily to decompose it. This is a u. So what we get the inner EU, and then the first part we need to find the derivative of the outer. This is the outer, take a derivative. That's what we need. This natural exponential, of course, is e raised to u, and because we know u, so per log is square root of x. Can you see? This is the first we need to put here. So we find that the first part is what is e. And raised to the square root of x power. Good. Now what is the second? You know the second is the inner. This is the inner. Take a derivative. We still do one more step. Okay, so now we put the answer is exactly the same. Why? Because the square root of x take a derivative is going to this 2 square root of x. Okay, and 1 over this, right? 1 times e raised to the square root of x is e raised to the square root of x. Can you see? Does these two answers are the same? Yeah, definitely, right? Definitely they are the same. Okay, so that's all for these most important topics. And thank you so much. And if you have any questions about this topic, please leave your comments. And if you like this video, you are very welcome to subscribe to my channel for more videos in the future. And the next video, and let's see, and we are still going to deal with the chain rule. However, we were just focusing on the prime notation. We will practice more about the prime notation. And thank you. I hope to see you next time. Thank you. Have a nice day. Bye.